Okay, so I want you to picture something. You're holding a coin, a regular quarter. You flip it, it lands on heads. Simple enough.
Right.
You think of that probability as just a number, 50%, 1 in 2. It's a static value.
Yeah, that's the textbook definition we've all lived with for, well, centuries. Probability is a measure. It's a bookkeeping tool.
Exactly. But what if I told you that probability isn't a number at all? What if it's actually a motion, a kind of physical path across some geometric landscape that we can't see?
It sounds like something out of science fiction.
Right.
But that is, believe it or not, the hard mathematical premise of the paper we're looking at today.
But it is a total mind bender. We are doing a deep dive into a paper that came out just a few days ago, January 26, 2026. It's called Geometric Classification of Scalar Probability Dynamics.
And honestly, it feels like these authors are trying to look right under the hood of the universe.
Why? They really are. They're taking this thing we all think we understand, randomness, and they're arguing that the difference between normal randomness, like rolling dice, and weird quantum randomness, it isn't magic.
It's geometry.
Curvature,
Yeah.
specifically, which is a concept I, for one, usually connect with Einstein and gravity, not coin flips.
And that's exactly why this is so exciting. They're taking that same mathematical lens, the kind of math used for relativity, and just applying it to probability itself.
Okay, so the mission for this deep dive is pretty clear then. We need to figure out why the universe seems to act so differently at different scales.
Right. Why does a radioactive atom decay in this smooth, predictable line while a quantum particle acts like a wave and interferes with itself?
And how on earth does geometry solve that riddle?
Because usually we just treat those as two separate kingdoms. You have the classical kingdom, population growth, chemical reactions. The rules are intuitive.
And then you have the quantum kingdom.
Waves, interference, the Born rule, and we usually just sort of shrug and say, well, quantum is just weird.
Yeah. Shut up and calculate.
Exactly. But this paper says, no, it's not arbitrary. The difference isn't the particle. The difference is the shape of the space the probability is moving through.
All right, let's unpack that. The paper kicks off by defining something called a scalar probability observable, which sounds terrifyingly technical.
It does, but it's actually pretty straightforward. Just imagine a function that tells you the probability of an event at any given moment. So like the probability that an atom has decayed.
Okay.
At time 0, it's 0%. An hour later, maybe it's 50%. That changing number, that's your observable. It's just a tracker.
So it's like a progress bar for reality.
A progress bar for reality. I like that. But here's where they make their first big move. They look at the empirical data from physics, and they notice that these probability tracks fall into two very sharp, very distinct classes.
They don't blend together.
Not at all. You get two flavors. Flavor number one is what they call ray type, or first-order dynamics.
Ray type. Sounds very direct, like a laser beam.
It is direct. The classic example is radioactive decay. You have a chunk of uranium, and the probability of an atom decaying follows this smooth exponential curve. It goes down, it never wiggles, it never goes back up. The paper calls it memoryless.
Memoryless. That's a strange word for physics. Does that mean it doesn't care about its past?
That is exactly what it means. In a first-order system, the future depends only on where you are right now. If I tell you the probability is at 50% this second, you know exactly where it's going next.
You don't need to know how fast it's changing or where it came from?
Nope.
There's
no
no
momentum.
perfect analogy. There is no momentum.
Yeah.
It's like pushing a really heavy box across a carpet. The second you stop pushing, it just stops moving. It doesn't coast.
Okay, so that's the classical world. Simple, straightforward. But then we have the other flavor, the quantum one.
The wave type or second-order dynamics. This is where things oscillate. You get interference patterns. Probabilities go up, then down, then up again.
And the rules here are totally different. Fundamentally, in this case, knowing the current probability isn't enough. If I tell you the probability is 50%, you can't tell me what happens next.
Because it might be on its way up or on its way down.
Exactly. You need to know the probability and its rate of change. You need position and velocity.
So it has momentum. It has what the authors call second-order closure.
Right.
So the ray type is the box on the carpet. And the wave type is, what? A pendulum.
A pendulum is a great way to think about it. If you pull a pendulum to the center, it has speed, it has inertia. It doesn't just stop at the bottom, does it? It swings right past that second-order behavior.
And that brings us to the core question of this whole deep dive.
Yeah.
Why the split? Why does some stuff behave like the box and other stuff behave like the pendulum?
And usually the answer is just, because quantum mechanics says so, which is circular. It's not a real explanation.
It's a cop-out.
It is. But this paper offers a geometric answer. They argue it's not about the particles themselves, it's about something called the geometric lift.
Okay, the geometric lift. This sounds like where we need to slow down a bit. The paper uses a shadow analogy that I found really helpful.
It's basically Plato's cave. Imagine that the probability we see, that number between 0 and 1, is just a shadow on a wall. It's a projection.
So we're just watching the shadow puppet show.
Exactly. The real action, what they call the lifted dynamics, is happening on some higher dimensional surface. And the behavior of the shadow depends entirely on the shape of that surface where the real flow is happening.
Oh, it's a landscape issue.
It's a landscape issue. And they established this flat versus curved rule. If the geometry where the real flow is happening is flat, like a sheet of paper, the shadow you see is ray type, symbol decay.
But if the surface is curved?
Then you get wave type, you get oscillation.
Okay, this leads us to what they call Theorem 1.1, the fundamental equation of probability geometry. It sounds incredibly important.
It's the backbone of their whole argument. The equation basically says that the acceleration of probability, how the rate of change is changing, is driven by the curvature of that higher space.
Can we translate acceleration is driven by curvature into just plain English? That's a mouthful.
Yeah, of course. Think about driving a car. If you're on a perfectly flat, straight, road zero curvature, you can just coast. You don't need to turn the wheel. The car naturally goes straight.
Right, cruising.
Now imagine you're driving on a curved surface, like the inside of a giant bowl. Even if you try to go straight, the geometry of the road itself forces you to turn. It forces you to accelerate in a new direction.
So the road is actually steering the car.
Exactly. The authors are saying that acceleration is the scalar shadow of curvature. If your probability is moving through a curved space, it cannot just move in a straight line. The geometry forces it to accelerate.
And that forced turn, when we see its shadow, looks like a wave. It looks like oscillation.
Precisely. A quantum particle isn't waving because it wants to. It's waving because the space it's moving through is curved, and it has no other choice.
That's kind of beautiful, actually. But here's where it gets really weird for me. I always assumed that oscillation was strictly a quantum thing, but the paper throws a curveball. They say classical probability can oscillate too.
Yes, this is the principle of quadratic geometry. And it is a bit of a surprise if you're used to just thinking about static coin flips,
They talk about something called the Bernoulli manifold.
which is just the space of all possible coin flips. And that space, believe it or not, has a geometry. It has a shape defined by something called the Fisher-Rho metric.
Okay, Fisher-Rho metric, what's that measuring?
It's basically statistical distance. How hard is it to tell two different coins apart? If one coin is 50% heads and the other is 51% heads, they're really hard to distinguish.
They're close neighbors in this space.
Right. But a coin that's 99% heads and one that's 1% heads, incredibly easy to spot. They're far apart.
So that concept of distance creates a shape.
It creates a shape. And it turns out the shape of this coin flip space acts like a sphere. It has a kind of springiness to it.
Springiness. Like Hooke's law for springs.
Exactly like that. A spring oscillates because its energy is quadratic. It's related to the square of the distance. Well, it turns out that probability spaces with this Fisher-Rho metric have the exact same quadratic structure.
Wait, so just the math of flipping coins creates a kind of restoring force that pulls the probability back and forth.
In a sense, yes. If you follow the straightest possible paths, the geodesics, through this space, the probability doesn't just sit still. It oscillates, and it follows a very specific law, the cosine squared law.
Cosine squared, that's the Born rule, isn't it, from quantum mechanics?
It is, and that's the huge takeaway here. The paper argues that this mathematical shape, this 2 cos of 2 oscillation, isn't uniquely quantum. It appears in classical mechanics with springs, it appears in classical probability, and it appears in quantum theory.
So the shape of the wave isn't the special part. It's a universal signature of this quadratic geometry.
Precisely. If you have a quadratic metric, you get cosine squared oscillations, the universal geometric rule.
Okay, but hold on. That raises a huge red flag for me. If classical probability can oscillate just like quantum mechanics, then what makes quantum so special? Why is the world of atoms so different from the world of coins?
That is the million-dollar question. If the geometry gives us waves in both places, where does all the spooky quantum stuff come from? The paper's answer is a hidden dimension. They call it the Hopf bundle.
The Hopf bundle. Okay, we're definitely getting into deep math territory here.
We are, but the concept is visual. Think about that classical oscillating coin. In that world, the phase of the wave, where it starts, is just an initial condition. It's optional. The space itself has no uh, bundle curvature.
So in the classical world, I can have the wave, but the phase is just a detail I can kind of ignore.
Right. But in the quantum world, the space is not flat in that way. It has what's called Berry curvature.
Berry curvature, it's like a twist in the fabric of the system.
It's a twist, and because of this twist, the paper introduces Theorem 6.7, the Hopf obstruction.
Obstruction sounds like a roadblock.
It means you are physically blocked from doing something. In quantum mechanics, because of this twist, you cannot change the probability without also engaging the phase.
Wait, so the phase isn't optional anymore?
It is topologically forced. It's locked in. Imagine you want to move the probability up or down called at the z direction. The geometry of the Hopf bundle is twisted in such a way that moving in z mechanically forces a rotation in the other directions, x and y.
Oh, I get it. It's like a screw. You can't just push a screw straight into a piece of wood.
Yes.
You have to turn it. The downward motion and the rotation are locked together.
That is the perfect visualization. The classical world is a nail. You just hammer it straight in. The quantum world is a screw. The geometry is threaded. Changing probability creates phase rotation.
That is wild. So the weirdness of quantum mechanics, the fact that phase matters so much, it's because the probability space is twisted like a screw.
In essence, yes. To sum it up, classical oscillation is geometry alone. Quantum oscillation is geometry plus curvature. And that curvature is what locks everything together.
This makes so much more sense of the why. It's just mechanics, but on a twisted manifold.
Exactly.
But there's another huge piece of this puzzle they tackle. Maybe the most famous equation in quantum mechanics, the Born rule.
Ah, yes. Probability equals the wave function squared. PP equals p psi 2.
And physicists have spent 100 years arguing about why it's squared. Is it just some random rule we have to accept? It always felt like a cheat code.
Just square it and it matches the experiment.
Right.
But this paper says, no, it's not random, it's rigid. They present Theorem 7.1, rigidity, and this is one of the strongest results in the whole paper.
Rigidity, meaning it couldn't be anything else.
Correct. They prove that if you want a system that meets just 3 simple conditions, the math uniquely forces the answer to be cosine squared. You have no choice.
Okay, what are the 3 conditions?
They're really logical. First, the system has to be bounded. Probability has to stay between 0 and 1.
Check. Makes sense.
Second, it has to be oscillatory. It has to be able to wave.
Check. We know quantum stuff waves.
And third, it has to have something they call dual closure.
Dual closure, what's that?
It basically means the system has to work as both a simple algebraic equation, like the ray type, and as a wave equation. It needs to be mathematically consistent from both perspectives.
And if you demand those 3 things,
There is only one mathematical solution, PP equals 2.
wow. So the Born rule isn't an axiom we just have to accept.
It's a geometric necessity. It's the only way to fit a wave into a bounded probability box that has constant curvature.
It really feels like they're rebuilding physics from the ground up, using geometry instead of just rules.
It does. They're shifting the whole perspective from probability as a number to probability as motion on a curved manifold.
So let's just recap this journey. We started with probability as something that flows.
The trajectory, right.
If the space it flows through is flat, you get simple decay, ray type, the shadow of a straight line.
The block on the carpet, correct.
But if the manifold is curved, you get oscillation, wave type, the car on the banked track. And the quantum world is special because it has that extra twist, that Berry curvature that locks phase to probability like a screw.
Which leads them to suggest quantum mechanics is kinematic.
Kinematic, as in it's just about motion.
Right. The wave behavior of an electron isn't some magical property of the electron. It's just the only way to move through a probability space that has that specific curvature. The electron is just following the road, and the road happens to be twisted.
That completely changes how you picture the subatomic world. It's not messy and chaotic. It's just curvy.
It is elegant, and it leads to some very provocative final thoughts in their open problems section.
Oh, I love the open problems. It's where they admit what they don't know yet.
Well, they hint that if this geometric view is right, maybe we could find higher order interference in the universe.
Higher order, like more than just the waves we already know about.
Exactly. Standard quantum mechanics assumes this curvature is constant and perfectly smooth. But what if it's not? What if we find deviations from the Born rule?
You mean places where it doesn't quite work?
Yes. If we found that, we might be detecting curvature defects in the geometry of reality itself.
Curvature defects in reality, so
Yeah.
glitches in the matrix.
You could think of it that way. If space-time can have black holes and ripples, maybe probability space has, I don't know, bumps in the road, textural changes in how randomness itself works.
That is a haunting thought. That somewhere out there, probability might not just be curved, it might be dented.
And finding those dents would be the holy grail of new physics. It would imply a structure even deeper than quantum mechanics.
It really makes you look at the world differently. We think of uncertainty as just a lack of information.
But this suggests uncertainty is a landscape that forces things to move in waves. We're all surfing the curvature of probability, whether we know it or not.
And that is something to think about the next time you flip a coin. Is it just landing on heads? Or did it just take a straight path through a twisted, curved universe?
It's definitely more than just a 50-50 chance.
This has been a heavy one, but I feel like I understand the why of quantum mechanics better than I ever have. Thanks for guiding us through the geometry.
My pleasure. It's a beautiful paper.
And to you listening, thanks for diving deep with us. Keep questioning the rules and keep looking for those curves. We'll catch you on the next deep dive.